topic of this lecture is open set. Okay, we already discussed neighborhood and interior point in previous two classes. Okay, now to define open set, we first consider a subset of real number. Right? So this is the definition of open set. We first take a subset S of R. Okay, consider S is a subset of R. Right? Now, if for all x belongs to S, x is an interior point. Interior point of S, then S is said to be open set. That is, we say that a set is said to be open set if all of its point is the interior point of the set. Okay, and alternately we say that a set S subset of R is open set if for all x belongs to S there exists a neighborhood of x, this is n of x, such that x belongs to n of x, this is the subset of S. Okay, and also we define open set. Alternately, we say that a set is subset of R, this is subset of R, is open set if for all x belongs to S there exists an open interval. Right? There exists open interval. We name this open interval, this is Ix, this is equal to AB. Okay, we write the open interval in the form of AB such that x belongs to AB, this is the subset of S, or this is contained in S and which is a subset of R. Okay, this is the set of real number. So we define the open set in three manner. Okay, this is the definition of open set. We can write any one of them, and using the last definition or last form of definition of open set, we easily prove an important theorem or important properties of open set, which is, it is very important problem or question of our exam. Prove that open interval is open set. Okay, and this is our problem, this is our question. To solve this type of question, we use the last definition of open set. So we take the open interval AB, this is S. Let the open interval AB, which is a set, we name this set is S. Okay, and let x be any point of S. Okay, and since x belongs to S, so by the definition of open interval, we can write that A less than X less than B. Okay, here A, X and B are three distinct real numbers. Okay, because A, B is open set, so X is not equal to A and X is not equal to B. And we know that from the density property of real number, there be infinite number of real number in between any two real number. So there exists C belongs to R and D belongs to R such that A less than C less than X, and we get X less than D less than B. Okay, hence we get an open interval C comma D, and X is belongs to C comma D such that X belongs to C comma D. This is also contained in S, and which is equal to AB. We give the name S, this is AB. And from this result, this is nothing but the definition of open set in this form. Okay, so we say that any open interval is an open set, right? Because any point X of this open interval is an interior point, right? So we prove that, or we can say that the open interval is an open set. Okay. Now if we consider some example of set, we first consider an important example. This is A, and this is 1/2, 1/3, 1/4, 1/n to so on. And we discussed about this set in previous class, that A interior, this is equal to phi. That is, this set has no interior point, because none of them or none of the interior point of the set. So we say that A is not open. A is not open set. Okay. If we consider any finite set A, this is x1, x2 to xn. Okay, and we know that finite set have no interior point. So we say that, or we can write A interior, this is equal to phi. So it is said that A is not an open set. If we consider the set of rational Q, okay, set of rational Q, and for the set of rational Q, we know that A Q interior, this is also equal to phi, because no point of Q is an interior point of Q. So we can say that Q is not an open set. But if we take the set of real number, all real number, obviously we know that R interior, this is equal to R, that is, every point of real number is an interior point of real number. So R is an open set. R is an open set. Okay, and if we consider a set A which is null set phi, and we know that phi interior, this is also equal to phi. That is, there is no point which is interior point of the set. But since this is a set which is null set, that is, there is no point of this set, so we say that the definition of open set satisfied by phi vacuously. Okay, so we say that phi is an open set. This is very interesting example of open set. Null set is always open set. Okay, and if we consider an open interval, here we already proved open interval is open set, right? Any open interval is open set. But if we take closed interval, we take closed interval AB, this is not an open set, because we know that AB interior, this is equal to AB. So the point A and B belongs to closed interval AB, but this 2 point is not the interior point of this set. So we say that all the point of this set is not an interior point. So this is not an open set. Okay, so this is the definition of open set. We say the definition in 3 ways, and these are some example of open set, and this is very important result regarding open set. Okay, and we discuss some important property and theorem of open set in upcoming classes. Thank you. Keep watching Math A to Z.